Alright, we are now on to uniform circular motion. So, I'm just thinking, because I think we might be going a little fast. Yeah. Well, how many questions do we have? 1, 2, 3, 4. Oh, we should be fine. Alright. Yeah, so I'll just explain what circular motion is. So we got uniform circular motion. It is an object traveling in a circular path with constant speed is said to be undergoing uniform circular motion, so such as the satellite orbiting the Earth. So as you can see here, say you've got like a stick with like a string that like goes out to the edge, and then you know, like when you're a kid and you got a ball on a string and you just like twirl it round and round and round like a helicopter. It's like this. So you've always got that equal force going in, and that velocity is always perpendicular to it going out in that one direction. Okay, so that is constant velocity just heading out in that direction. So now we need to define the concepts of average speed and a period. So velocity for circular motion is defined as 2 times pi by the radius divided by the period. And those are all measured in its respectable units. So velocity is measured in meters per second, and then you have the radius of a circular path. It's measured in meters, so that will be this distance here along the dotted line. And I'll just give you a little legend here. So this is our radius. Obviously you've got the velocity there, and then you've got the period to do one rotation. So it's like to go from here all the way around back to that. That was such a bad drawing, but you get the idea. To do one revolution, to do one rotation, it takes so many seconds. So the object's velocity at any point is directly tangent to the circle. Okay, so the magnitude equal to the distance covered in one complete revolution is divided by the time taken. All right, so the velocity will be higher if less time is taken, or if yeah, so it's like you have to have that ratio right between the radius and the time. So say you complete a radius in a very low amount of time, then that means you have a greater velocity. But say your radius may be bigger, but it's taking you just as much time. So say to go in a radius, to go in one revolution where the radius is like a meter, and it takes you 3 seconds to complete it, then, you know, that's like our base, right? But say it takes you 6 seconds the next time round, that means your velocity has decreased because that ratio has then decreased. So the radius and the period here really work hand in hand. So it's just a matter of, yeah, make sure you got your units right when you calculate it as well. But you might get some questions where you might get a graph on the external, and they might say, compare the radial distance with the period taken, and you might say, the greater the radius, the more time is taken, or the smaller the time is taken, the greater the velocity. But yeah. And you might do not a research investigation, but an experimental investigation, and you might use circular motion. You might measure the amount of time that it takes to do certain revolutions at different distances, and then you might graph that and compare. It's just an idea, but I saw some people do that. It is quite hard the more distances you do, but it's just to, prove those theories, that the greater the radius, the more time is taken, yada yada yada. It really depends on how you choose to write those predictions. Alright, now we're going to look into a couple more definitions here. So we've got centripetal acceleration and centripetal force. I'm just going to get some water. Okay. Yep, so centripetal acceleration, it is calculated using that formula. Acceleration is equal to velocity squared over the radius. And that's the acceleration towards the center. So acceleration, once again, is measured in meters per second squared, whereas velocity is measured in meters per second, and then obviously the radius of the circle is measured in meters. Whereas you've got centripetal force, which is measured by Newton's second law, F equals ma. There must be a net force directed toward the center to cause this acceleration, which is called a centripetal force. So this centripetal force, the formula then becomes mass times velocity squared divided by the radius, the force of which is moving toward the center. So just like how we have here, this is that centripetal force. Yep, so that's measured in newtons. Once again, our velocity is the same, the radius of the circle is the same. So now we're going to do this question, and this covers the criteria that's above that. So solve problems involving average speed of objects undergoing uniform circular motion, and solve problems involving forces acting on objects in uniform circular motion. So it's really integral that you understand how to do these kinds of questions, because they are multiple step. Everything we're doing today, all these questions are multiple step questions. When you start getting into the more theoretical stuff that you'll find in Unit 4, like, what's it called? I forgot what the topic's called. Not quantum theory, although that's interesting in itself. What is it called? It's like the one where you've got like twin A goes off to outer space and then comes back. It's where you've got like the different perspectives. You know what I mean. You know what I mean. And if you don't, then you will see. You've got some topics where it's quite conceptual in the way where you've got to like answer it in sentences and stuff, whereas the content we're covering today is much more mathematical, and you have to remember lots of little things when doing these calculations, such as for inclined planes. What is net force? What is force due to gravity? Vectors, it involves magnitude and direction, or for circular motion, what the different forces are and where are they moving. Yeah, and there's a lot of different formulas to remember, but most of them, I should say, are in the formula sheet. But yeah, that's just something I just want to point out. But yeah, if you have any questions about that, feel free to ask. Without further ado, I think we'll just get started with these questions. So we've got about 1, 2, 3, 4 questions left for today. But I do want to say as well, if you feel confident in doing these questions, if these are topics you've already done before, by all means go ahead and do them and then check your answers as I go. But if you haven't done these before and you feel like you should have, or you're just worried about them, don't stress, because it is still very much early days. You've got months and months until you have the exam, and this is stuff you may not even have covered in school yet, so I wouldn't stress too much. But yeah, just do what you can, and hopefully most of what I say makes sense. But once again, if you have any questions, feel free to ask. And if there's something you're not so sure about, but you want to go ask your teacher, take a photo, ask a friend, check your textbook, check the ATAR notes resources if you have access to them. But yeah, all the support you need is around you. So yeah, we'll just get into this question now. So a car with a mass of 1,000 kilograms travels around a roundabout radius of 10 meters at 60 kilometers an hour. So we've got our radius and we've got our velocity. Calculate the acceleration of the car while in the roundabout. So first things first, I just want to convert this into what we need, which is meters per second. So, so to put that into meters, we need to go 60 times 1,000, so it's going to be 60,000. So now we're in meters per hour, but we need meters per second. Yep, and there are 60 minutes in an hour, and there are 60 seconds in a minute. So it's going to be divided by 60 times 60. So divide by 60 times 60, so it's going to be 360. So now we're going to end up with this calculator. 1.66.67, I'm going to say. I feel like that's very fast. Is that too fast? Doesn't look like it. If there's anything wrong, or if you notice anything wrong, feel free to put it in the chat, because that would be good to know. I'm sure this wouldn't have been the first mistake I made, but I checked all this beforehand, so we'll see. I think we'll just go with that number, because if you think about it, there are 60 minutes in an hour, so you divide it by 60 to find it for 1 minute, and then you divide it by 60 again to find it for a second. So that looks fine. So we're just going to say that it travels at that. Alrighty. Yeah, so calculate the acceleration of the car while in the roundabout. So we have converted all that. It's now, let's put down A. So we're going to use the formula acceleration is equal to velocity squared over radius squared. So now I'm going to put that number 1.66. Oh wait, no, sorry, 166. Ooh, sorry, I'll just erase that. The reason why as well we converted that to meters per second is because that's how we talk about velocity in physics. but also because our radius is in meters, so everything has to be relative. Divided by radius squared. Yeah, so 10 squared, so that's just going to be 100. Yep. So that's going to be... Put it into the calculator. That's going to be 277.79. Meters per second squared. Now for B, I'll use a different color. They say to calculate the net force on the car. So for this, we're going to use F is equal to MA, or F net, I should say. Alright. So we're going to say it's 100, oh not 100, sorry, 1,000 multiplied by 277.79. Yep. And that's going to be a very big number. That's going to be 2,770. Oh, wait, no. It's a very long number. It's going to be 277,788. .89. And this is an approximate, by the way, because I rounded. Once again, that's going to be in newtons. So a lot of force. Yeah, and there shouldn't be any errors there because it looks like all the units are right. But if you spot any errors, feel free to sing them out because it would be good practice for you. Now we're going to go on to C. So calculate the time the car takes to go around the roundabout. So put C over here. Now we're going to calculate time. So we're going to use the formula V is equal to 2 pi R over T. And that's another reason why we converted our velocity to meters per second as well, because our period is measured in seconds. So that was 166.67, so that's what we're going to put over here. It's equal to 2 pi. Oh, and our radius. Pretty sure it was 10 meters. Yep. And that's over time, or the period. So now we multiply both sides by the period, our unknown variable. But now we need to divide both sides by 166.67 to get the period by itself. So now it's going to end up being 2 pi times 10 divided by 166.67. Cool. Now I'll put that into the calculator. I'm just thinking, for this part, put your calculator into radians because we're dealing with pi, yeah. So 2 times 2 pi times 10 over 166.67. That is going to be 0.37, and that does not look right. What happened there? If I put in degrees, does it change anything? Probably not. No. Okay, apparently it takes no time at all, and it's 0.37 seconds. Or 0.38 once we round. Something's happened there. Something meant to be squared, actually. Well, apparently it's full text. The only reason why I would see an error would be in our conversion in the beginning. But everything seemed okay after that. Yeah, because if you think about it, 60 goes to 60,000 because you have to multiply 60 by 1,000 to get from kilometers to meters. And then to go from hours to minutes, you divide by 60, but then you divide it by 60 again. So unless that's something that happened there, that would be it. Oh, would you look at that? Okay, yeah, don't do what I did and divide by 360. Divide by 60 and then divide by 60 again, because otherwise you'll get the completely wrong answer. I was actually meant to go one more decimal place over. Sorry to be annoying. Learn from me, learn from that mistake. I was like, these numbers are a little big. Just a tad big. By about a 10th factor. Yeah, so it's actually going to be like that, which makes so much more sense. So now I'm just going to go through and quickly change everything. So sorry if you've written it all down in pen. Hopefully you used pencil or a pacer. But yeah, we'll just fix that up now. And I'm going to do it in a different color, which I am currently, so that you can see the change. Sorry for the confusion. You're all probably in the chat going, finally, she noticed. After all that doubt. But hey, I'm human. Everyone makes mistakes. Good thing I picked up on it eventually. So that's actually going to be 2.77, but it's actually going to be 2.78 by the time we round. meters per second squared. I'll change the thing over here. And then our answer's going to change down here as well. Yep, so it's going to be 2.71. I mean, 78. Okay. Yep, so that's going to be 277, and I also just kept that number earlier from in my calculator, so it's going to be 2778.89. That's our force. Now here, where we went wrong, well, I went wrong, not we, I, is here. So hopefully we should end up with a much larger distance, not distance, time. And also, if your numbers ever look funky, always backtrack. So always do what I did and just backtrack and just double check, because, well, you saw what happened. It could save you a lot of marks. It could really just be a little savior in itself, and just, you know, might be the difference between getting that A or B. So I'll just get rid of that. So what was it again? It was 1 point, wait, why? Oh, it is, sorry. 16.67, yep, okay. And this was not squared. Don't know why, I just did a little dot there. Ignore the dot. 16.67. Alright, hopefully that's a bit of a better answer. So, back in radians, not that it really makes a difference. Well, at least for this question, for some reason. Times 10 divided by 16.67, and hopefully we get a better answer. There we go. Takes 3.74 seconds, and that looks a lot better than 0.38. Alright. Now we're up to D. What would happen to the force required if the car speed doubles? If friction between the tire and the road is unable to provide this much force, what will happen to the car? Okay, we'll deal with the first part of that question first. And we're going to do it right next to B, because it's talking about the force. So I'll get green, and we'll redo it here and see what happens to the force. So F net is equal to mass times acceleration I'm just realizing the car speed doubles. Okay, so say this is the speed, right? So this actually needs to double. Oh, okay, so we actually have to do a couple things. Sorry, I'm going to backtrack again. We're going to calculate acceleration again, and then force again, with that new speed, that doubled speed. And we're going to do it in green. So D, and that formula was A is equal to V squared over R squared. Yep, so it's going to be in brackets 16.67 multiplied by 2 squared over the radius squared, which is just 10 times 10, which is just going to be 100. And that should give us, oh, no, I don't know what happened there. Alright, that gives us, I just put the wrong number in, hold on. That's better. Alright, that gives us 11.12 meters per second squared, yeah. And we can compare that to the last one. So it's significantly like a higher rate than the previous acceleration when velocity gets doubled. Now let's see what happens to the force. So the force it's a mass, so mass times acceleration. And our mass will be, what's her name? 1,000? Wait, is it 1,000? Yeah, 1,000. Multiplied by that acceleration, which is 11.12. And we get 11,120. Newtons. And let's compare it to the old one. We had 2,778.89, whereas we've got that here. So we could always do a bit of a ratio of that just to see how it changed. So we could always put, seeing as velocity 2 is now greater, we could always just do like v2 over, sorry, I put that little 2 in the wrong spot. I'm not actually trying to square it, I'm just trying to do a little ratio comparison. v1 over v2. So we can always get the first answer and put it over the other one. Yeah, because we need to answer that first question in like a word answer. So we could show that ratio and say, well, according to the mathematics that we've used, it, you know, triples or something like that, which is why we're doing this little ratio. You could always do v2 over v1 or v1 over v2. We could do both and just see which one we prefer to say. So that v1 is going to be 2778.89. Yep, and then we're going to put 11,000 at the bottom. I'll just see what we end up with. Alright, we're looking at 0.25, so it's like a 25%, it's like a quarter. So V1 is like a quarter of V2. So it's like we're looking at 1 over 4. So I think just based off that, it'd probably be nicer to show V2 on top of V1, just so we can say, hey, it's like 4 times the size. So 11120 over 2778.89 78.89. Yeah. Yeah. So we could say like a word answer, and I'm wondering if I can actually type. I can't. But what we can use, just by doing a little ratio comparison like that, we could say the force required as the car speed double. When the car speed doubles, the force required by the car multiplies by 4, goes up by 4. It goes up by a factor of 4. But yeah. Now to answer the second question, if friction between the tire and the road is unable to provide this much force, what will happen to the car? Well, this is essentially just about the concept of speeding. If you go too fast on a road that can't handle that much force, that much acceleration, the car will go out of control and just spin and eventually crash. Yeah, which is why on roads we have speed limits, because those roads can only handle so much. That's why when you go over a speed bump, you can only go about 20k an hour, because if you go any faster, you'll end up being a bit of a flying car for a few seconds, and then you'll cause some serious damage to your car. That's why these speed limits are important, and that's what this question is getting us to understand. If we provide too much force in a place where the speed is too slow for that secondary speed, then yeah, the car won't be able to handle it and it'll crash.